that's your line. Sorry, Neil. Take it away.
Good evening, everyone. My name is Neil Pandia. I would like to welcome you all to the 13th Cyberspectrum meetup. This event series serves as a forum for the exchange of knowledge and ideas related to software-defined radio, and generally aims to get people interested and excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your software or hardware background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. The event here tonight is being sponsored and hosted by Edis Research. Our first speaker will be Martin Brown, who will give us an update on what's new in the GNU Radio world. Martin is a longtime contributor to the GNU Radio project and is the GNU Radio community manager. Most of the stuff that he touches is SDR related, and his day job is writing software for Edis Research, where he spent a lot of time developing RF knock, among other things. Our second speaker will be Trip Humphreys, who will give a talk titled Interrogating Passive Wireless SAW RFID Sensors with the USRP. Trip will discuss the SDR design with the B200, including custom FPGA modifications and external RF components. Additionally, a brief overview of SAW sensors will be given, and various signal processing, post-processing techniques will be discussed. Trip is a PhD student at the University of Central Florida in Orlando. His research interests include wireless surface acoustic wave sensors and software-defined radio applications. He joins us remotely from Florida tonight. We would like to thank him for staying up so late to give his talk. Our third speaker will be myself. We will begin a series of hands-on introductory SDR tutorials using USRP hardware and GNU Radio software on the Linux platform. In this first installment, we'll review SDR concepts, explore the USRP hardware, walk through the installation of UHD and GNU Radio on an Ubuntu system, and construct and run a few basic flow graphs to get familiar with GNU Radio.
Sorry, if you don't mind my interruption, you'll look behind you.
Yes, that's me.
But if you look very, very closely, Neil likes to stand under the tree.
Subtle Photoshop. All meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The previous 12 events have already been posted in full HD video. We have set up a channel on IRC called #Cyberspectrum on Freenode as a way for people remotely watching the live stream to contact the group here in Santa Clara with comments or questions, and to alert us to any audio-visual problems. Future meetup locations will alternate every month between here at the Edis Research office in Santa Clara and at Noisebridge in San Francisco. The next meetup will tentatively be held on Wednesday, March 9th at Noisebridge in San Francisco. Further details will be posted on the meetup page about 1 or 2 weeks prior to the event, so please tune in, pun intended, for all the details, including a list of speakers and presentation topics. As always, if you'd like to present something or if you have ideas about future topics, please let us know. We would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would especially like to thank Edis Research for providing the space, hosting the meetup, and providing complimentary pizza and soda. We'll now get started with our first speaker. Thank you.
Thank you, Neil. And just for you out there in Webland, I'm sorry I wasn't following with the slides. Please submit a talk for next time, and join us on IRC #Cyberspectrum on Freenode, and remember this URL for next time, and watch that Twitter handle for updates. So thank you, and now we will begin with Martin Brown, who's going to give us our GNU Radio update, and I will load up his most amazing, creative, incredible, no, that's the wrong one. Most amazing, creative, incredible slide deck. How good is that?
Yeah, I'm on a private crusade trying to use every tool there is to make slides, and just using a legal pad and a chopper.
What have you done so far?
Oh, it's a long list now at this point.
Are you documenting it?
Yeah. Well, I listed them all on Twitter once. I think that counts. And most of them are actually crap, so I still have to find a good tool to make presentations. Yeah, so like I promised Twilight, I do a regular update on free software, radio stuff, and I haven't been very good about it, but yeah, here's another one. So I just picked random things that recently happened, and I'm sort of going to highlight them. You can obviously ask me questions, but this is sort of a selection of things that I knew. So first one is GNU Radio release 3791 is coming this weekend, and am I not in the picture? Like, is this better? Okay. Yeah. So we'll be releasing 3791 this weekend, which means the downloads will be available by Monday, including the live USB, DVD, or the ISO image. It's a bug fix release, but we had some pretty big bug fixes, some really important ones. So I don't want to go into details, but this one is worth checking out. Yeah, this is great. Can you do this? I don't even have a way to. Thanks. Okay, now this is something that is really interesting, I think. So PyBombs, who knows what PyBombs is? There's actually not a lot of people, so when I say, oh, we released a new version, you might not care, but you should. So PyBombs is a tool. I keep forgetting what the acronym stands for, but it's a tool to make it easy to install GNU Radio or UHD, and especially all the out-of-tree modules. So it's kind of like a package manager, like apt-get or yum, or pip maybe is a better, or gem, like it's maybe a better analogy. It's not quite the same though. It's sort of, so the O is like overlay, and I don't know, I forget what it stands for. But it'll use all kinds of tools available to actually facilitate installation. So for example, you can tell it to install GNU Radio from source, but install all dependencies as binaries, and then put them on your system. So we released version 2.0 because version 1 was basically sort of, it came out of, I'm not quite sure where it came out of, but so Tim O'Shea wrote version 1, and it sort of became very popular, and people started using it, and it really couldn't handle all of our demands, so we updated it. And version 2, it does all kinds of cool things. So, for example, it's easy to install. You just have to do pip install PyBombs, and then you get it. And that seems like a standard software feature, but we didn't actually have that in PyBombs 1. And it can do all kinds of things, such as you can install GNU Radio like 5 or 6 times in different versions. So you can have an embedded version and all that, and you could be running RFNOC, for example. And PyBombs will just automatically let you do that. Something else that's interesting is you can define your repositories for recipes. Now, a recipe is an instruction on how to install something, and we provide recipes for all the out-of-tree modules, GNU Radio, etc. And the first thing that's interesting is we actually split them up. We made sort of like the most important out-of-tree modules and base stuff, and then sort of the extra ones that might not compile with every version of GNU Radio, we sort of put them into a separate repository, like Multiverse and Universe in the Ubuntu package world. And yeah, we have a bunch of features. Oh yeah, cross-compiling, very easy, sort of built into PyBombs. So if you want to do RFNOC, for example, on an E310, it used to be a bunch of steps, and like now it's just one command or 2 commands, something like that. So we just released it, so it's guaranteed to have lots of bugs. The only way to find them all is have lots of people try it on different platforms. So this current version does not have Mac OS X support, but we're working on that. That was also something that didn't work. But all kinds of Linuxes are already supported, and then OS X coming soon. Yeah, so please try it. And even if you're not actually using all kinds of out-of-tree modules, maybe you're just using UHD, but you need to build it from source, this might actually help you. So this is really, really useful. Okay, thanks. Okay, GRCon 2016 has been now finally officially announced. It'll happen in Boulder, Colorado in September. So the last GNU Radio conference was a fantastic conference. Everyone said so. So I mean, this is definitely my personal opinion, but everyone who came And I talk to agree that it's the best conference we had so far in terms of content and also location. So maybe you're wondering why we're changing the location. Well, we don't want to be stuck at DC all the time, so we wanted to go somewhere else. And I think Boulder, Colorado is a great place. So the university is hosting it, but there's also other things to see in Boulder, like NIST is there, for example. And we're targeting about 250 attendees. Now, the last GNU Radio conference was great for many reasons, but it was also great because we've been working on improving the conference. And I think we're still the same team, so I think this is, we're on a good trajectory. So I don't see any reason why this shouldn't also be a fantastic conference. So, like, oh, I forgot the website, I'm so stupid. It doesn't matter though, if you Google GRCon 2016, you'll find it. Yeah, so registrations aren't yet available, but yeah, will be so soon. Yeah, that's that. And FOSDEM happened last weekend, so why am I talking about it? So, because it's a great event. FOSDEM is the Free and Open Software Developer European Meeting. Is a annual event, happens in Brussels, it's always in the same place. And this is all kinds of things open source and free software. And for the third time now, we have an SDR track. So FOSDEM is grouped by tracks, and then they, they have a common theme. Like there's a Python one, Mozilla, and high performance computing, and software-defined radio is one of those tracks. And I'm one of the organizers of that track. And we had a completely packed track. So it was difficult to just organize the timing and the scheduling on that, but it's like we've covered all kinds of areas like hardware and academic problems, machine learning was in there, really, really, really excellent talks, and they will hopefully be available, so you can watch the videos soon. So we might have had some issues with the video in our room. I hope it wasn't too bad though, and if not, then we'll have on the FOSDEM.org videos available for you to watch. And actually, I just remembered. So the Chaos Communication Congress was like annually. It's always between Christmas and New Year's, and they also have the videos up already since the Congress. So if you like watching videos of nerds talking about interesting topics, like both those events will be worth checking out. I think I have one more slide. Oh yeah. So I thought this would be a nice sort of category to add, is like the random projects of the week, like project that sort of stuck out to me personally. So the first one is SRS UE. SRS is actually a company from Ireland that make LTE software, like among other things. SRS UE is a project I actually saw at FOSDEM for the first time. It's really, really cool, and it's available in source code, and it's a full UE for LTE. In free software that, for example, works with the B200. Very, very cool. And I don't know if you know GR Paint, so if you do not, you should check it out. It's really fantastic. But it was recently upgraded quite significantly. And in case you didn't know, there's this website, cgrand.org, which is a list of all the out-of-tree modules that are currently available for GNU Radio. And it's constantly updated, uses the PyBombs recipes as a backend. So it's easy to add stuff, so we'll always have a pretty accurate count of current out-of-tree modules, so that's definitely the place you should check out. Okay, that's it from my end. Yeah, and I'll do another update in a couple of months. Thank you very much.
Thank you.
If there's any questions, this is not a very technical talk, but okay.
What is GeoPaint?
Oh, okay. So it's an out-of-tree module that lets you paint pictures into the spectrum. So if you have a look at the waterfall diagram of the spectrum, you'll see the signal someone else put there. You can, and it loads random pictures, turns them into one. I'm not quite sure the actual, like Chris, you've used it, right?
Yeah. So it'll take an image and run it through an OFDM modulator so that you can paint an arbitrary image into a waterfall output.
Yeah, it's pretty nice. Especially if you're using phosphor, for example, to actually view it, you just it's very high quality. I don't know, anything else?
Nothing online. Oh, there was a question Shevdor asks regarding PyBombs, is there a quote-unquote PyBombs list?
Yes, there is. So to list available. I mean, it's difficult to dialogue with the delay and everything. I'm just going to sort of give a broad answer. So yeah, there is a command called PyBombs list, and it does several things. It'll list all the packages you have installed. It'll list all the packages that are available, and for every package that is available, it can tell you how it's installed. If you install it from source through apt-get or however. Yeah. So, wait, is this? Yeah, this is up to date. So, but there is actually a manual. If you click that link, the GitHub. So, the reason you have to click the link is because it's sort of included in the source code. So, can you click this? And so we currently ship the manual with PyBombs as a markdown file. As soon as it loads, we'll have it.
Oh, is it loading?
No.
What's going on?
I don't know. Doesn't matter though. You type PyBombs help and it'll give you all the available code.
It's redirecting here.
Oh, okay. Yeah, there we go. So, yeah, if you scroll down, then you'll see there we go. So it explains most of the steps. Thank you, Internet, for that question.
There was another one, which was a comment, perhaps? No, it's a question from myself. Very funny. Yeah, this presentation package he used to make his slides, is that open source?
Yes. Well, actually, I don't know. Like, how do you make those legal pads? I don't know how to make those legal pads. And I guess it's just making paper, and that's a well-documented thing.
Yeah, what about the font? Was the licensing on your font?
Oh yeah, you can copy the letters from the slides. That's fine. But like, even making a Sharpie, I'm not quite sure how to do that. So, you know, it's actually like now more that I think about it, it's really it's quite yeah. I think pencils are easier to make. So, but I don't know. Well, I think it's kind of philosophically. So,
Well,
you had a question?
Well, basically, I think I on the internet may have been asking whether there's a discussion list on PyBombs.
Well, it's discussed in radio. It's the same one.
Okay, so well, there's nothing specific.
No, we don't have a special one. I mean, people have been using the PyBombs issue track on GitHub to report failures of all kinds, and that has been very, very useful. I've actually gotten like 5 pull requests in the last 2 days or something like that. So, yeah, that's very nice. So I'm happy that people are contributing back and fixing the bugs on their system. The problem with PyBombs is it has so many options and like combinations of configurations that you can use. So it was like, for me as the main author, it was impossible to test them all, especially across platforms. So I have my Ubuntu laptop, and most of the commands work on that, but that doesn't mean they still work on a Fedora system. So I'm hoping that people with Fedora systems will give it a try and then give me some feedback. And we actually fixed the Fedora bug today. When I say we, someone else fixed it, and I clicked the pull request merge button. So you had a question?
The question is, why doesn't GNU Radio just use apt-get, for instance?
Oh, you can use apt-get for GNU. There's nothing wrong with that, except you won't get the latest version. So where it gets difficult there is you use apt-get, it'll also use UHD from apt-get. And unless you have, it's tricky. So you want to use RFNOC, for example, you need your own UHD. But then you can't use apt-get anymore because you already have UHD, unless you sort of go through some hoops. But if you're just starting with GNU Radio, there's absolutely nothing wrong, and it is actually the recommended method to get started. Just do apt-get install GNU Radio, because that's guaranteed to work. But it's not guaranteed to give you an up-to-date or latest version. Yeah. And the other reason apt-get is not necessarily problematic, but where it falls short is that it'll install GNU Radio, and it'll work fine thanks to Maitland, who does all the packaging for us. But GNU Radio really only gets interesting when you add out-of-tree modules. You can't add those through apt-get. So then you have to do a manual from source installation of those out-of-tree modules. And you can do apt-get for GNU Radio and then install the rest through PyBombs, also works. So, hey. Yeah, so that answers
Hello.
that. mentioned the website before. So this is Cgrand, lists all the out-of-tree modules, and it's very nice. You can search for stuff, and if it's in here, then it's easily installable through PyBombs, and there's all kinds of different, interesting projects in here. So the thing about GNU Radio is we try to sort of focus on sort of core components, communication, etc. Whereas here you have all kinds of esoteric out-of-tree modules. Some of them are, so the quality is, varies, but I think that's fine because people write their own little project and they just upload it and then it's available for everyone else. So we don't have some kind of ranking and a rating system in here. That would be nice. But most of these actually compile and do something useful. And just to point out some, we have here the crypto, radar, DRM for digital radio, Piano for machine learning and stuff like that. So there's tons of these. I'm not sure how many, but like more than 50 at this point. It's very, very nice. It's a lot of extra functionality for GNU Radio. Some of them are actual tools. So PyQt adds the plotting stuff, and like event stream, for example, actually adds scheduling mechanisms, and others are just purely application driven, like the radar stuff. Oh.
You said there were no ratings. Do you have like a metric of number of downloads?
No, you can go to GitHub and then look them up, but some actually don't go through GitHub. So for example, like everything from Osmocom, they use their own server, so we don't have access to those stats. But Cgrand is not really set up to track that because the hosting of the code and the this site are sort of separate entities. Yeah, a rating would work because then it's still localized to Cgrand. But you could also rate stuff through GitHub. So.
You consider using like Arch's user repository model, which has ratings and spaces for comments on each package and something?
Well, someone has to implement all of that, so probably not.
I mean, you brought up the word rating, and they said, "Oh, here's a structure already done."
Yeah.
It's a lot.
I mean, this sort of ties into our recipes, etc. So
Yeah.
we'd have to add it, and then it would be nice, but so one thing that personally I'd find more useful is if it shows you if it actually compiles with your current GNU Radio version, or like the latest GNU Radio version was tested with, that kind of thing. Yeah. Okay, thanks. Thank you, Martin.
All right, so we'll do a very, very quick show and tell if that person is still willing. Chris?
Oh, I mentioned to Bola that I had a literally 5-cent hack to improve my SDR experience, and that was crazy gluing a nickel onto the back of my laptop so that I could,
Can you show it for everyone?
so that I could magnet the antenna on. So now I can walk around with a very nerdy big, laptop, and nobody sees me just standing there. I'm playing on my tablet. No, actually, I'm sniffing with the antenna magneted to the bottom. 5 cents. Actually, 3.5 because it's a Canadian nickel.
Is it magnetic?
Yep.
Thank you. It's the simple things, right? Okay, so now we're going to actually cross to our other presenter tonight. Somebody's busily hacking away in the background to demonstrate GR Paint. So we'll do that when we can. Who else has a USRP here, or some SDR that's capable of transmitting and has something to transmit? No? All right, maybe a little bit later then. Ooh, actually, Neil does.
Yay!
But Neil's going to be on a little bit later this evening after the trip. So what we're going to do is we're going to cross to Trip now, and then get him up on the big screen. So if you want to grab another slice of pizza or something, this will just be a minute, and then we can get going. Yeah.
Oh, I know. I pay attention occasionally.
Yeah.
I haven't actually.
It's wonderful when Windows open source is really by the way, so yeah.
I know.
You worked for one, now he's got one, and now you just blew your compass.
30 years from here. It's going out of style.
Hey, Ian. Hey, man. Good to see you.
Yeah, so I've got a road
I hope I was okay
that's cool.
broadcasting your beta thing on Twitter this morning.
That's cool.
Okay. All right, he's a good guy, you know, but I realize I've kind of let the cat out of the bag. I figure you've had it out for so long now that you've done the secret. All right. Did I spot? You look more organized than normal. Far more organized than normal, even. Okay. Bit of a cluster in traffic coming down, but.
You made it.
Yeah, I made it. Bit of surface street diversion.
Now this is something that we just focus on.
That's my general reaction to San Francisco. Yeah, really nice.
I have a system problem on my Mac at the moment where I don't have audio on Anchor. When I'm not using my monitor. When I'm using my monitor, it's okay. When I have the Mac, somebody else said this as well.
Because I sometimes I have to switch to Safari.
That's right, trips to Florida, I forgot that.
Trip, can you hear me? Yeah, so what I'm going to do now is I'm going to just change the audio.
Hey, good to see you.
Good to see you too. Hey.
And yeah, just one.
No, it's a hoodie. It's cool though, what can I tell you, man?
It's nice and
Yeah, it's all nice and
Wow.
dark and
High
mysterious.
quality.
So the
Yeah.
audio should come through the.
London fashion.
I'm going to mute myself on this one, and I'm going to unmute it on the one.
But I'm lacking the Patagonia.
You want me here?
Can you still hear me?
It's chaos.
Trip, can you hear me?
If you want to see some GR paint, you want to see some GR paint stuff, just go to my Twitter page,
Oh, okay.
Dr. MPEG.
Yeah, let's
I am the author of GR paint, but
that's great. Derek's just trying to do a live demo, but I figured maybe during intermission we could do that.
like dozen images that you can.
Yeah. So yeah, let's do that. We'll try and put it in our picture. Yeah, well, I can hear you. Can you hear me?
I haven't talked to
Trip, can you hear me? Can you hear me? Right. Can you make it so that your voice comes through the slide presentation hangout? Okay, you know what? I think we can get around that.
I'm the same way.
Yeah, all right. I think we can.
Early 80s.
That's part of the problem.
Political aspects.
He's a nice guy, he's very professional.
Yeah, if we would sort of probably give it some of the ancient history.
Second Street.
Not to ideas when we were on
Okay. And then almost there. One last thing to do.
I've never been to the release
Trip, can you hear us? Why is there feedback? There shouldn't be any feedback. One.
I have friends all over.
Have you got two computers joined the Hangout?
Oh, wait a minute. What's this one?
Keep track of what's going on.
You can't, if you have an extra Hangout.
Oh, you know what it is? It's this one.
You can't mute the output from a Hangout. You have to use the computer.
Yeah, why is this kid?
Coming on the computer. So,
But in the summer, why do you have to go on daylight savings time? It's still at 7.
Trip, can you hear us?
What's the time of why?
Now I can't hear you.
Okay. So we're going to have to do half duplex because I have to either mute you or mute here. So I'm talking now. I'm going to switch back to you.
Okay, I can move the presentation over to this computer, so you only have to have one Hangout.
No, it's all good. We're all set, so we can see you, and it's all good. So I think with that, I'm just going to add it so that the live stream people can see it, and then we should be good.
Be good. Okay. Start when you tell me to start.
I will wave my hands like a frantic person. So what I'm doing, I'm just adding a local capture of the screen on this laptop so that everyone can see it on the internet.
Okay. All right, I'll go ahead and start. Thanks again, everybody, for having me out tonight. I really appreciate it. It's getting pretty late over here on the East Coast, so if I fall asleep, just go to the next talk or something. So I just wanted to come out or present tonight our work here at UCF, interrogating passive wireless Sol sensors using the USRP. Again, my name's Trip Humphreys, and I'm a PhD student here at the University of Central Florida in Orlando. First, I'm going to give a brief overview of our research activities here at the university. and then talk a little bit about our passive wireless Hall sensors, and then go into our implementation of the USRP to interrogate those sensors. And then I'll try to do a quick demo over here to show you that. So at UCF, we are mainly focused on surface acoustic wave devices. We do everything from the design and analysis to the modeling all the way up through fabrication. In the past couple of years, we've been working with applying surface acoustic wave devices as sensors, and that's where we're working now. So about 10 or 15 years ago, the motivation behind getting into sensors was that NASA was looking for a way to detect moisture underneath the space shuttle tiles. And now I'm sure you can imagine that it's a pretty big deal to have wires and bulky, materials underneath those tiles that are very heavy and require all kinds of penetrations. So they asked our research group if we could develop a wireless sensor system that doesn't require wires and can be operated forever without the use of batteries or energy harvesting. So just a little background on SAW devices for those who don't know. So it's just a solid state device that converts electrical energy into a mechanical wave on a piezoelectric substrate, and then vice versa. We can convert that mechanical wave back to an electromagnetic wave that we can again measure. We can do very complex signal processing because the SAW device is literally a spatial mapping of a sample time function. So here on the bottom, you'll see a picture of a basic picture of a SAW device. On the left is an input transducer, and on the right, an output transducer. This device would act as either a simple delay line or just a very simple filter. So we have filters, delay lines, resonators, and more recently, sensors and RFID. So SAW sensors, like I said, is more of a recent field of application for these devices. So basically how they work is they're a one-port device. All we're doing is measuring a reflected response from the SAW device. So instead of that second transducer, we'll have reflectors on the substrate. The SAW device allows us to modulate the incoming signal and reflect it back to the transceiver, so we can modulate frequency, phase, delay, or amplitude, or any combination of those. It's very similar to radar. We send out an interrogation pulse. The SAW device is attached to an antenna. The SAW device allows us to modulate that signal, reflect it back to the transmitter, and then we post-process it and extract the sensor information. The sensors can operate from 10 megahertz to 3 gigahertz, limited by fabrication tolerances. We're working at 915 megahertz for our experiments. They're totally passive. Like I said, it's just a reflection, so no batteries, no energy harvesting. They can operate over a wide temperature range, cryogenic up to 1,000 degrees C, depending on your material choices. There's a variety of measurements, so temperature, strain, and gas have been shown by our group, and we're working on others. And then a variety of device embodiments. Resonant CDMA are more prevalent. We've been working on a technique that we call orthogonal frequency coding to encode the information and tag our device with an RFID. So orthogonal frequency coding, it's a spread spectrum coding technique that we've been using to encode our SAW devices. So basically we have a sequence of SAW reflectors that we'll call chips, each with a different center frequency. We shuffle those in time. That gives us a code. It has high processing gain and time and frequency diversity. So the other advantage of the SAW device is that we can build in a large acoustic delay. So like in a wired system, we can multiplex our sensors to have many, many sensors. Well, here we can time multiplex them with a delay line. And so on the bottom here, this picture you'll see on the left is the input transducer. It'd be attached to an antenna. The input will propagate along the substrate, bounce off the reflectors, and back out the transducer, back out the antenna, and we'll receive that signal. So here I had a quick animation, but I'm in a PDF form now, so I'll just kind of explain what's going on. But on the receive end, we use a match filter correlator to extract our information. So basically, we start with the designed device layout, so we know the frequency of all our reflectors, we know the delays to all those reflectors, and along with some other information. So we use that to generate a baseline match filter, and then scale the frequency and time delay to generate a bank of match filters that will correlate to some temperature change or some change in strain. So we take our received response, correlate it to this entire bank of match filters, and then whichever one provides us with the strongest correlation, we say that's the correct signal, and we correlate it to, like I said, a temperature or strain measurement or whatnot. So here, I'm just showing a couple of different sensor embodiments. This is a temperature sensor. All it is a SAW device packaged and then soldered to an antenna. So most SAW substrates are inherently temperature sensitive. So we can exploit that and measure a frequency shift and correlate that to a change in temperature. We built high temperature sensors. So the challenge there becomes more a materials challenge and an antenna integration challenge. So a colleague of mine, Mark Gallagher, was working on this, where using exotic substrates such as langotate, which has a very high melting point and is very stable, and working with another company to actually direct write antennas onto the substrate. So this top picture here on the top right, right in the very middle is the SAW device, and then you'll see the meandering dipole on antenna that was direct written with copper directly onto the substrate. Another embodiment that we've developed is the hydrogen sensor. So this one is a little bit more unique in that we'll use a thin film to determine a hydrogen concentration impacting the device. So we lay down a hydrogen sensitive thin film in our delay line. That film reacts with hydrogen and changes in resistivity. That resistivity causes amplitude changes that we can measure. And again, we can take those amplitude changes and correlate that to some hydrogen concentration. On the right here is a test done the top right is a test done at NASA, where they were testing hydrogen concentration on 3 different sensors. And on the bottom is just a simple illustration of the sensor. So on the left is a reference delay line, and on the right is the measurement delay line. And another sensor embodiment we have is a strain sensor. So like I said, that these devices are inherently temperature sensitive. They're also inherently strain sensitive. So by bending the device, we can cause a velocity shift, just like the temperature shift would. And again, we can correlate that to some change in strain. So on the top right here is an illustration showing I can take the actual SAW die, glue it down to say steel beam, strain that steel beam, and extract the strain on that beam. So on the bottom here, in the light blue or kind of teal color, is a commercial strain gauge that's wired, and then the dashed orange line is one of our wireless strain gauges. So you see it's almost very similar measurements. So that was just a little brief overview of the sensors themselves. Afterwards, if you have any questions on how they work, I'll be happy to answer those. But I'd like to talk more about the interrogation system itself. So in the past, nobody makes a Sol sensor interrogator that you can buy off the shelf. So we are building, custom units that were kind of connectorized components. We started at 250 megahertz, and that prototype you can see on the top right. So you can see it's pretty large, pretty bulky. The antennas are even bigger, as you can imagine. And then we got better at kind of integrating and putting all that together. So we moved up to 915 megahertz, and so on the bottom left is another completely custom interrogator. This one sends out a noise pulse and then listens for the sensor echo. And then as of pretty recently, we've been working with the software radio, the USRP, for the last couple of years. We've used that to implement our interrogation system, and with that, it comes with many advantages, being that we don't have to be building interrogators and spending a lot of time doing that when we'd rather be doing sensor work and surface wave device work. So our interrogators have some pretty, I'll say, specific requirements, especially with our orthogonal frequency coding. So we need high bandwidth, and we're working at 915 megahertz. So with the high bandwidth, we can add more chips to our Sol design. That gives us better processing gain, just like you would do in a radar application. And we can also optimize our reflectors on the device a little bit better. And additionally, we need some kind of way to synchronize our transmit and receive so that we have a definite T equals 0 for every measurement. A precise listen window. So here we'll listen for about 10 microseconds after the transmit pulse. And with that, we need to be kind of coherent so we can integrate multiple interrogations to improve our signal to noise ratio. So while it has those strict requirements, it does pose some unique design challenges. Like I said, we need as much bandwidth as we can get, which is difficult for some streaming applications. So with the B200, we want all 56 megahertz. So like I said, it's very difficult to get that, with a continuous stream of data. And it's difficult to synchronize the transmit and receive channels in a way that is predictable from interrogation to interrogation. So, signaling over USB is fairly slow, where, our devices all respond within 10 microseconds. And then we need to be able to trigger our TX and RX states with very high accuracy so we can pulse our transmit and then control our RF switches that we put out there. And then we have microsecond transmit pulses that we'll send out, and I'll show all that a little bit later. So our solution that we've been working on for the past few years is to implement some custom functionality in the USRP FPGA. So on the transmit side, we implemented an interrogation signal generator, so this host computer no longer has to, be responsible for sending transmit samples. And then that will also control the RF switch that is external to the USRP. So we can switch between a single antenna, transmit and receive. And on the receive side, we have a module that synchronizes to the transmit pulse and then buffers a single interrogation cycle worth of data into a block RAM, and then reads that back out at a slower rate. So we don't have to keep up with that 56 megahertz sampling rate, which is fine for us. We don't need the continuous stream. Here is just a block diagram and a timing diagram of our FPGA modifications. So on the top here, you can see our interrogation signal generator pretty much stripped out all the transmit DSP and send it to the AD 9361 on the B200 or the 9364 on the new B200. When the interrogation signal is finished, it sets a flag. The receiver goes into a receive mode, where initially it has a small delay built in. That delay is just to clock out any samples that are already in the registers on the FPGA. It will write 512 samples to RAM, which corresponds to about 9.15 microseconds or so, and then reads those samples back to the host, where we'll post-process it on the PC. Here is just an example showing our transmit pulse. So this is a 1 microsecond linear FM sweep, or just a chirp. On the left is the in-phase and quadrature components versus time. Here it's a 35 megahertz sweep. On the right is the spectrum showing what we predicted, the teal dashed line, and then what we actually got from the USRP and the orange solid line. So we got very good results with that. We've also been experimenting with using a random noise pulse for our interrogation signal. So we've been trying a linear feedback shift register network that generates a random sample each clock cycle. Again, that's a 1 microsecond pulse. So right now we're kind of qualifying that and making sure that works as intended. And that's for some special applications for the DoD and whatnot, where they don't want to have a determined signal sent out that's exactly the same every time. Here, showing just the transmit pulse, measuring the 1 microsecond pulse, and then on the top and then on the bottom, you can see the pulse repetition interval, which is adjustable on the host CPU by setting some settings. Here, it's about every 265 microseconds it'll pulse the sensor, and then wait for that received signal. And then finally, to improve the performance just a little bit, we added a few external components. So an amplifier on the transmit, so we could have some, a little bit greater output power. So we're about plus 20 dBm now. That gives us a little better range, or better sensor accuracy if you're close up. And then after that switch, or after that amplifier, is an RF switch, which is controlled by the GPS DO port on the B200. So we use that switch to switch between the transmit and receive antenna. And that gives us some pretty good isolation, so we're not saturating the receiver every time we pulse the antenna. So if we had two antennas, that direct response between the transmit and receive antenna would saturate us almost every time. Here, so I'll take that schematic from before and show a picture here of the internals of our system. So on the bottom, we have just the USRP B200. On the top left is the RF switch. Top middle is our transmit amplifier. And then top right, we have a power distribution, power switch, the amplifier, some fans, and an LED. So it's all pretty simple there. And then the enclosure is a custom enclosure that we designed and had fabricated by Protocase. And so I'll switch over here. So this is the front and back of the enclosure that we designed. So on the front is just the antenna port. And then on the back, depending on which embodiment of the system you're looking at, this one in particular has a embedded computer inside, so all the post-processing is done within a single box. But here, we have video out, USB for mouse and keyboard, Ethernet port, and just power and power switch. On the other embodiment, you would just have a USB port to connect to the host computer. On the host computer, we have all our post-processing. So we're doing a pretty simple gathering of the data. We have a USRP sync in GNU Radio, and this is all written in Python. Excuse me. And so the USRP sync, just to program all the TX parameters. On the receive side, just a USRP source, a head block, and a vector sync, so that we can stop the flow graph after we get a determined number of samples. So I'll ask for 512 samples per sweep times the number of averages I want to do. And then we'll reset those blocks on each iteration. And then we pass that data into our signal processing routines, our match filter correlator. That'll extract the temperature, and then this will get plotted or sent out as a text message to display temperature or strain or whatever it is that you might be measuring. So just a little bit about the system itself. So like I said, they're integrated into custom enclosures, about 2 to 3 pounds right now. We're looking to get smaller and lighter. 2 embodiments that we have, one that requires an external host computer, one that requires nothing but just plugging in a mouse, keyboard, and a video. Output power is about plus 20 dBm. The range to the sensor, we've tested to about 7 meters so far. Of course, you could use a higher gain antenna or a bigger amplifier and get even farther range. Reading time varies depending on, the host PC that you're using. For one average, we can do a reading about every 40 to 80 milliseconds for 1,000 averages. And there, I mean, we ping the sensor 1,000 times, take all those, average them together. It takes about 400 milliseconds. And all in all, the whole system itself costs less, than $1,100. In the past, like I was saying, we were building these fully custom interrogators, and they were many thousands of dollars. So, we have a great advantage, especially as a small research group with that. Just to show some of the sensors that we designed to work with the system. So we have 4 sensors that are designed to fit within the specific bandwidth. So they operate at 915 megahertz and have a bandwidth of 28 megahertz. On the right here, you can see their time response, each labeled in a different color. So here you can actually see their discrete time slots that each sensor resides in, each having 4 chips. So we'll tell the software which sensors we're expecting. It'll go in and time gate and process each sensor individually. So like I said, 4 sensors here, all at 915 megahertz. Here is just a single wireless sensor measurement. So I believe here the range was about one or 2 feet. And then I have attached a thermocouple that's wired, just as a comparison for the extracted temperature. So here you can see it matches very well with a thermocouple reading. And then averaging multiple sweeps. So with just one average, you'll get a pretty variable measurement, a spread of about 1 degree C, and that depends, highly on your signal to noise ratio. If you average, say, 1,000 sweeps in black, you get a much more stable and accurate reading. And then, of course, you can use multiple sensors at once. Here's a plot just showing 4 simultaneous sensors and extracting the temperature from all 4 of them. An interesting thing you'll see is this sensor, kind of blue in the middle that's going up and down, is actually responding to interference from other sensors as their time delay changes very slightly. It'll move into an adjacent sensor time slot. So that's one of the disadvantages we have, but you can overcome it with some design changes. And then, so currently we're working on, improving our device embodiment, adding strain gas detection to our Python code. We've demonstrated that using MATLAB. But we're trying to integrate it all into one software package now. Better user interface for when we deliver these. Currently looking to deliver these to the DoD and some other companies. Working with the B200 Mini now to get even smaller and hopefully faster. So on the right, you can see a picture of the B200 Mini, and on just below it is one of our sensors with the antenna. So the radio itself is almost smaller than the actual sensor, which is pretty exciting. Like I said, we're looking to improve speed and accuracy, so hopefully offloading more tasks to the FPGA. The end goal being kilohertz rates for data acquisition, and then real-time statistics of the sensor responses. So I'd just like to thank, I'd like to acknowledge, of course, all the graduate students that work in our group, especially Mark Gallagher, Dan Gallagher, who did a lot of work with me on the software radio system. Our external support from Dr. Youngquist and Dr. Cy Wilson of NASA, and my advisors, Dr. Maloka and Dr. Weeks. And then I'll switch over to a quick demo now, as long as everything's still going okay. And switch over there. So here I just pulled up the user interface that we have. That we're using. So this main window here will show the extracted temperature of the device. So I have next to me, and I'll try to show you guys in a second, I have a sensor and the system wirelessly. And over here in this second window, I'll show you we have our all received data. We'll deconvolve our interrogation signal, show you some frequency response, and then I'll show you some debugging tools that we have built in. So I'll go ahead and start it just so we can start seeing some things. So I'll switch over to the kind of debug window now. So on the top left is our raw data that we received from the USRP. The first little pulse that you see is the interrogation signal. So normally we don't like that to be there, but we can use this as a reference signal to deconvolve the interrogation signal from a received response. So you see this big bulk of data at around 4 microseconds, or it's about in the middle of that plot. That's the data we received, but it doesn't look anything like the plots I showed earlier. So we take that reference pulse, deconvolve it, and this second plot on the right shows the deconvolved data. So you can actually see each individual chip now of the SAW device. And I'll move the device around a little bit. You can see I'm moving it away now, so you can see the amplitude fall, and I'm moving it closer to have the amplitude come up. On the bottom right, or bottom left, excuse me, is the frequency domain response. And then on the bottom right is an interesting plot. So this is actually the peak correlation from each of those matched filters. So right now it's locked into room temperature. So what I'll do is I'll switch to the temperature window now, and you can see a couple of spurs there as I move the sensor away and our signal noise ratio died out. But I'm going to heat the sensor up now with just a heat gun. And you can watch the sensor reacts in real time with the applied heat, so you can watch it go up and then it'll just self-cool back down. Let that go for a second, and I'll try to move.
Everyone's having a good giggle here. I don't know whether you can hear me, but hopefully you can. Everyone's enjoying it.
Okay, I can hear you now. So I'll try to kind of show you real quick. I'll bring this over here. So there's the sensor and then the system over there, so you can see. And then I'll bring the sensor up here. So there's the sensor tag with antenna, and then the device there is just there in the middle. And then I had another interesting thing that I'll show you real quick. So we had a student in the past. Like I said, these have some interesting applications. he took one of those, that exact antenna and sensor, embedded it in concrete, and you don't have to have any wires coming out of the concrete. So for like applications where you want a corrosion sensor on a bridge or whatnot. So I'll switch back to this debug plot real quick. I'll move my sensor out of the field of view there. So if you kind of pay attention to the beginning of the plot there, you'll see kind of a spur just after the interrogation pulse, and I'll put this big cement block there, and you'll see a sensor response come back. So we can actually interrogate the sensor that's embedded in concrete, or you can embed it and some other material. So that's a kind of application that you could have. So we're investigating that for some civil uses. But apart from that, that's kind of the end of the demo and presentation. I can take any questions that you might have.
How about a round of applause? That was excellent. Any questions from our audience here? Question?
It looks like on your computer, especially if you have this
Would you mind saying that rather loudly in this general direction?
what kind of a switch do you use? And do you use some kind of an integrated semiconductor-based switch or a relay?
Sorry, could you repeat the question? Sorry, my speakers aren't very good.
Yeah, do you use a semiconductor-based switch or a mechanical relay?
Let's see. So I have the switch here. Yeah, this is a CMOS switch that we use. So it has it's maybe 50 nanoseconds of switching time, so it's extremely fast, and it has pretty low insertion loss too, so we don't take a big hit on our noise figure.
I've just put the word out to our viewers on IRC. I might add that they're quite numerous. I think we probably had is that a secondary reflection bouncing around the sensor substrate, or on that note, do you quote unquote terminate the acoustic energy at the other end of the device? There are a couple of questions, but I'll let you do that one first.
Okay, so yeah, that is a second echo from the device itself. So it'll go out the transducer, hit our reflectors, bounce off. Some of it will go back out the transducer. Some of that back does another lap, goes back to the reflectors and back again. So we call that a double transit. I try to optimize my device so if I make a long initial delay, I can avoid that double transit falling back on top of other sensor responses, and that'll kind of distort the extracted response that you'll get. So good question.
Okay, and then there's one more, which is, that's pretty impressive. How much power is the interrogator putting out to be able to communicate the sensor in concrete? Wondering if it could be scaled up to an actual full bridge with sensors.
So that is, we're putting out plus 20 dBm, which is fairly low output power for us. We usually work at about a watt, but yeah, you could scale up the output power. One of the applications people are looking into is putting the interrogator on a truck and then driving it down the bridge and interrogating these sensors successively to kind of get an idea of the condition of the bridge, whether it be strain or corrosion or whatnot.
Okay, great. I just realized that it's quite possible that the people on the live stream didn't hear the questions, but hopefully you gathered the rough context from Tripp's answers.
So yeah. So any other final comments or questions from the audience here? No, it doesn't look it. But we all enjoyed that a lot. That was really excellent work. So one more round of applause for Trip. And also for hanging in there and staying awake with us. Thank you very much.
No problem. Good night, everybody.
Oh, hang on. Sorry. Let me. I was just giving you a moment for a last word, a goodbye or good night, or it looked like you were saying something.
Good night, everybody. Thanks for having me. I appreciate it.
Okay, see you later. Good night. Thanks a lot. A bunch of people on Twitter are clapping too. You know how you do /me is clapping? Yeah. All right, see ya.
There aren't that many hangouts at once. All right, so let's take just a couple of minute break, and then we'll conclude with our final session with Neil. I don't know about you, but I'm going to the
More people with HDL than parallel. Oh man. They should. That's funny. Only program and then I started Verilog. Okay. A couple of little things I kind of borrow from HDL. Other than that, I don't know. You could get excited about it. Before you cross it. The support. Start off easy, tear me apart.
Someone's gonna mind it. That needs a keeper. Someone to hold the chain.
It is, but you need someone else.
Well, that's it.
James, do you want to take me?
Well, I was working on a robotics project with a friend of mine, and was considering doing a startup with it. You know, it's kind of go to grad school, so started to kind of
Kick around.
yeah.
Going on around here. Everyone, short stuff.
And I was kind of planning on going to Cuttington for a little while longer anyways. It's not like I was like, pick and choose, and I have a couple of consulting things, so yeah, it's not so bad.
Yeah. This isn't one.
Extra time to pursue.
Yeah, we won't.
Yeah, that's your time, you know. I find the trick is to actually make sure that it's because like as soon as I go to town, I wasted it all again.
Yeah. Well, maybe you work, you can put on some friction side. For the company, maybe it's expensive. Like $675. Yeah, sure.
Don't worry, in 30 years we'll get the bomb back together. Let's shoot.
Yeah.
The next lap. Right.
I don't think anybody's have any idea where it is. I don't even have any idea where it is.
Anyone cares anymore.
Well, it was a lot of fun while it lasted.
I think we were more successful. We got to that point where like,
Hey, well,
we're going to do this thing.
well, yeah, that's true too. And especially, you know, Dennis has some very optimistic thoughts about like how much dish time people are going to be willing to kind of donate.
Right.
And I don't know if that would have happened.
If you got it close enough, I mean, I had the dishes were getting it close enough. You're still on expensive dishes.
Especially about that month after we figured out the propulsion system wasn't working, but they were still kind of trying to convince everyone that it was still alive for some reason. Actually, I just read some places too, you can find an abstract something and publish it.
I've got to switch to video.
All right, so we're good.
Hey, Derek, did you go? Okay.
Yeah, we have it running.
All right, let's do it.
Sometimes it's 445 megahertz. I mean, it's separated. Oh.
It's pretty high. Just the SDR server, they usually run Windows because a lot of people watch like this Windows Zone. Other than that,
He's running the awesome window manager, which I don't consider awesome.
I haven't played
No
most of
clue
that stuff.
where
I'll
he's
say
taking
that a lot of the people who are doing the sort of hobbyist SDR receiver things are doing Windows Zone.
Where's Dr. Ampeg? Do you want to come down and do a really quick spiel on what it's about, and we'll run a demo?
Go to my Twitter page.
VMs are terrible because you know,
I don't know if they were
designed to
super ideal for the spacecraft or orbits that
Okay, do you want to run it? Derek.
I can't figure out how to do it. I need all of it from back. I need the drivers. Yeah.
I've actually worked there.
well, like I said, it's already happened. And I think, you know, it would have cost, there would have been a cost associated with it. Yeah, not sure.
There you go.
I played with Windows long enough.
Those are all GQRX pictures. Here's a good one. Elizabeth Taylor.
I tried to play it. Not sure.
No one gets this.
Okay, so just very quickly before we begin our next slot with Neil, this was referenced a little bit earlier. So Ron, aka Dr. Ampeg, sitting up the back there, has been working on this incredible project. You might have seen little signs of other people hacking on similar sort of stuff if you think back a couple of GR comps, but Ron has basically taken this and made it super duper high, very high fidelity, really. And
it works better in GQRX, for one thing.
And he's recommending GQRX, but what it essentially lets you do is take an image and it will synthesize the RF so that when you transmit it and then view your transmission in a waterfall, such as with GQRX as he recommends, you will actually see your image rendered on the waterfall. So I'm just going to show you his screen captures, which is posted on his Twitter account, which is Dr. Mpeg, DRMPEG. So these are things that you can actually see on the waterfall in GQRX as he's broadcasting the synthesized RF of this photo. So, but what's the trick with this particular one? We said not many people might get it.
Oh, it's the guy in Jefferson Airplane died last week.
Oh, right. In memoriam.
Also, that's a hack to GQRX to do a black and white waterfall.
Right. That looks stunning.
That's
I think we all get this one.
Yeah, that's for the next. That's for the next GQRX picture. There we go. So it's 4K OFDM, so you're getting more than one carrier per pixel usually.
Wow. 4K OFDM. Very nice.
I love cartoons. This is there we go.
Wow. Hey.
There you go.
My man. I should point out that the leading engineer on this project that I had the pleasure of working with is actually sitting in the back of the room. Mr. Austin Epps, there he is. Control the space probe. Good times.
Are you receiving?
I'm not, but I can.
We're in a pretty good occasion.
You said 5 megabytes.
We're also licensed.
I'm just imagining the bloody FBI down the road at the stadium getting all that
Thank you,
shit
5
set up.
megabytes. Oh, we're the perfect place. Right?
That's the last time they get it again.
What the heck? Screw you guys! We'll have a helicopter flight over.
Yeah, it's even better. Take a picture of the helicopter and then transfer down there.
How's your game?
Oh,
yeah, no, there it is. Here we go.
You could do framing grabs.
Eric, are you still here?
There you go.
What?
Bottom line is that you got paid.
It's interesting. That's definitely the plot.
Why is it?
That's exactly
It's overflying like crazy for some reason.
That's the frequency.
Max.
400,
Terrible.
45 megahertz.
There we go.
You know what? Neil will probably be able to do a better demo.
What's
So
a
character.
Well, it's a 16K FFT, right? What size is he transmitting?
There we go.
Derek, what size OFDM are you transmitting?
No, I mean it was zoomed out, but
The image width is
USRP
1920. It's 1920. Try that.
Eric, we should talk later about USB performance under OS X because I found that it's absolutely terrible.
It's gotten worse. Come out with newer versions.
Really?
Yeah. Mavericks.
It actually just got a hell of a lot worse when I plugged the second display in. I'd not experienced that before. All right, so I reckon a bit of a round of applause for Ron because this is some really stunning. So thank you, Ron. All right, so let's get on to our next speaker. I'm just going to give you the video. Neil. So Neil is going to go through a bit of an introductory session on SDR and how you can get set up with SDR and using GNU Radio. And what we're going to do for the live stream viewers is actually show his desktop on the live stream. Can I show you your desktop?
Yep.
Okay, there we go, audio. I'm going to move my mouse, but I'm just going to make the thing a bit bigger on the screen. Okay, how's that?
Okay. Ready? Okay.
Take it away, Neil!
Okay, thanks. So I'm Neil, and I'll be talking about a hands-on introduction to SDR with USRPs and GNU Radio. I think for a lot of you this may be stuff that you already know, but for some of you, hopefully here in the room and out on the internet, this is new and helpful to you as you ramp up and get familiar with USRPs and GNU Radio. And this is supposed to be interactive, so the first part of what I'll talk about will kind of just be slides and going through some background material information. And then the goal, I don't know if we'll have time or if everyone's ready for it, or if, just make sure this thing is still recording. If everyone has their laptops, we have a couple of USRPs up here if you didn't bring your own, and go through the exercises together and make it kind of a hands-on presentation. And this is part of a series, so this is the first one, and we'll be following up over the months with successive talks that'll go deeper and deeper into GNU Radio and look at different applications and different aspects of using it. First thing I'd like to do is thank my colleague Nate Temple, who was very, very helpful and instrumental in putting this talk together and helping me with some slides. Nate gave a presentation about his Etcha SDR embedded device a few months ago, back in September at Cyberspectrum, and you can learn more about that at the link here. So a special thanks to Nate Temple for his help. So what is SDR? Again, this is an introductory talk, so it's meant at novices and beginners. What is SDR? So a radio, the definition varies, but generally speaking, people will say it's a radio in which some or all of the physical layer functions are implemented in software, usually running on a microprocessor, but also an FPGA. And that software that runs on a CPU or FPGA is running some kind of DSP or communications theory algorithm to process samples. That's where the name software-defined radio comes from. And most radios today that are fixed in nature and have a specific function or a set of operations, a fixed set of operations, use a classic super heterodyne receiver architecture. So in that architecture, the RF signal from the antenna is mixed with a local oscillator to produce an intermediate frequency, shown in the diagram here below. And that IO frequency is then what's filtered and used for demodulation. With SDR, a direct conversion receiver architecture is used, and this is also called 0IF, and it has a couple of other names as well. And the reason for the name is because the architecture eliminates the intermediate frequency by translating the band of interest that you're trying to capture directly to baseband. And the frequency of the LO is set to the same frequency as what your signal, your transmitted signal is set to, your desired RF signal is set to. So why use SDR? There are a couple of reasons. Most radios are hardwired to specific frequency bands and communication protocols, and they can't be changed easily. They're kind of like a black box, and you can't really probe inside and see what's going on. You don't have access to internal state information or other values, and you just have to take the outputs as they're presented to you. With SDR, you have a lot of flexibility, upgradability, reconfigurability, and lower cost. It's flexible because you can reprogram the radio to do anything, almost anything you want, within the limits of the hardware, of course. So if you have a radio that's capable of it, 1 minute it can operate as a FM transmitter, the next minute as a GSM base station, for example. Upgradability, meaning that you can change the software and you can change the functionality of the radio, fix bugs and things like that if there's something wrong with the processing that you're doing. Along the lines of upgradability, you have reconfigurability. You can change the functions of an FPGA or the software that's running and reconfigure something. Even if it's running the same waveform, you might have a change in the way something is reconfigured. And then lower cost, because the components that you're using are generally simpler and lower cost than in a fixed black box traditional radio. There are a lot of applications of SDR. The term was first used by Joe Maitola in 1991. SDRs go back to the 90s and the 2000s when they were used as voice band soft modems or WIN modems. US Robotics, a company that used to make modems, had a product line or a trademark name for WIN modem, where a lot of the signal processing was done on the host computer in Windows, and the modem itself, the hardware itself, was pretty bare bones, just converting between analog and digital. Cellular handsets often use software-defined radio, such as on the baseband processor inside the handset, like, say, a Qualcomm Snapdragon processor. SDR can be used for cellular base stations, and there are a number of projects or companies that are working or selling software for this. There's OpenBTS, which is from Range Networks, but it's also an open source project that people freely use and can contribute to. And there's several others. There's SRS LTE, which was mentioned earlier, The authors presented something at FOSDEM. There's a couple of other projects. OpenLTE is open source. There's Eurocom. Marisoft is closed source. It's from a company. It's not free, but it's a very mature LTE stack that uses software-defined radio, and it's very stable and robust. Other examples include GPS receivers and simulators. There's some open source projects that implement receivers, and there's some companies that are working on simulators. Two notable companies that I'm aware of are Skydale Solutions and Navigation Laboratories that make GPS simulators, constellation simulators, actually multi-constellation simulators. Adaptive and cognitive radio astronomy, satellite communications, ground stations and such, wireless security research and spectrum monitoring, and wireless prototyping and testing. Those are all common applications for SDR. Most SDRs have some of these tool chains, use one of these tool chains, including the USRPs. Processing can be done in real time or offline, some kind of post-processing. For the USRP radios, there's something called UHD, which I'll talk about in a minute, but basically the USRP driver presents an API, and you can program that directly in C++. And most software-defined radios have some kind of native API that you can program directly. And then there are other frameworks. We'll talk about GNU Radio. That's the whole point of this series of talks. GNU Radio is open source, and under the hood it uses Python as well as C++. And you can program it directly in Python using libraries like NumPy and SciPy and Matplotlib to do mathematics and to do plotting. There's LabVIEW from National Instruments, which is a visual tool. And there's MATLAB as well as Simulink from the MathWorks. That's pretty popular and widespread. And then there's several tools that I'm not very familiar with, but they run on Windows, and they, I think, cater more to the ham radio community, or they seem to be centered around the ham radio community. HDSDR, SDR Sharp, SDR Console, WinRAD, and I think there are others too. All of these are Windows-only based programs, and they also, when used with USRPs, they use UHD through the XDIO interface. Getting into some of the things that we'll need, some of the tools we'll need to work with USRPs and GNU Radio is Git and GitHub. And maybe most of you are familiar with this already, but maybe not. And Git is basically a source code management system, kind of like Subversion and CVS before that, back in the day. But Git is a distributed source code management system, and it's pretty widespread, and probably most open source, or many open source projects have migrated to it. GitHub is a web-based hosting service that hosts Git repositories, and most or many open source projects like GNU Radio and UHD are hosted on GitHub. When using Git, you have the choice of a command line tool and a GUI tool. What we'll do here in this series is use the command line tool, but there are also many GUI tools for Linux and Mac and Windows. In this series, we'll assume that people are using Ubuntu, and so you can use the apt-get mechanism to install packages, and sudo just means that you're running something as root. And so to install Git, which I don't think it is installed by default with the ISO that you would download and install. So you just would run sudo apt-get install Git at a command line terminal window, and Git would install. And then you would type git clone, and that would pull down a repository, that would clone a repository. And then you can use tag-L to look at all the tags or releases of a given project. And then you can use git checkout to check out that particular tag. I also include commit here because every time you change something in Git, there's a commit associated with it, a hash associated with it. You can check out by that as well.
Can I just add something there? Do you want to just maybe do a git tag-L on GNU Radio or UHD?
Sure.
I mean, I know that quite a few of you are experienced with this, but I have a feeling some of you are not really. Does anybody want to actually run this on their laptop as they're following along? Because I can see some of you have it out. I guess if you need any help trying it out, then just raise your hand, but don't feel shy. But Neil's going to demonstrate some of this, and you might actually want to just make the font.
Oh yeah, right.
Just do Control+.
Yep.
Outside the menu.
Sorry.
I have a question.
Is it not working?
No.
On the terminal.
Yeah.
I have a question.
Yes.
Is all setup can run on virtual machine environment?
Yeah, it can. Yep. You can use VirtualBox or VMware. Yep.
A lot of people do that, but if you need to do any really high bandwidth stuff to your SDR, then you'll pay the cost.
Particularly with USB, the virtual machine network interfaces tend to be pretty reasonable. Obviously, you'll still hit processor overhead, but USB works poorly on virtual machines.
Is that big enough or a little bit bigger?
Is this swapped? That's control, right?
Yeah, it should really be. Try the other one.
What have you done with your? Oh, you know, it's your window manager or something. Must be because it's works on works on Mac. Windows.
Really?
Yeah.
I don't know. Maybe it's. Anyway, is it still too small?
Like you have to make it like real.
Okay.
Really big.
Oh boy. Okay.
Where is it?
Under edit preferences, and then appearance. Set that to that big.
There we go.
Is that better?
Yeah.
Okay.
Maybe
Cool.
HTTPS.
What is it?
Just go to a repo that you've already got and
I don't have one. I started from scratch in this.
HTTPS.
Crap. What is the URL again?
Yes. / UHD.
Yeah. Trying to get all this to fit on one screen. There we go. Yeah.
Double click the where it says terminal.
Okay.
Oh, I didn't run it yet.
Why is it so slow? Okay, there we go. Okay, so now we did the clone. And so now we have a repository UHD. And now if I type you can see all the tags for UHD. And usually all these tags are just releases and they go back quite a ways. The latest version of UHD is 3.9.2 and that corresponds to this tag here. And if I wanted to check out something else, I could just do git checkout and then pick another tag like, this is acting very strange. Are you not seeing anything on the screen?
It's off the bottom.
Sorry?
It's off the bottom.
Yeah.
Yeah, that's good. Up. No, it just drags me.
Okay. Okay, so this is not working very well.
Just drag the entire window. Yeah, that's it. No, it's too far. Watch that when you.
Yeah, right.
There we go.
Okay. So I just checked out release 3.9.0, for example, here. I'll go back to release 2 because that's what I'll use in this demonstration. So that's using Git. That's using Git in a nutshell. And that's how you change between versions. And if you ever need to go back and build a different version, you just change the release that you're using and rebuild. And we'll go through the build process in a few minutes. Let's talk about USRPs and look at some of the hardware. The USRPs are made by Edis Research. It was a company that was founded in 2004 by Matt Edis. It was acquired by National Instruments in 2010. This is the headquarters, this building here. This is where most of the work and activity around USRPs happens. The USRPs have 4 primary families of radios, of devices. There's the B series, the N series, the X series, and the E series. The B series has 3 models that are current and active: the B200, the B210, and the B200 Mini. And the B series, the letter B is meant to denote that there's a USB interface to the host. The N series has 2 models currently used. There's a N200 and N210, and the interface is Ethernet. There's the X series, the X300 and 310, that have a 1 or a 10 gigabit Ethernet interface. The difference between these, like an N200 and a 210 and X300, X210, is the size of the FPGA on the device. Other than that, the 2 radios are the same. And there's also an embedded series where you don't need an external host computer, and inside the device is an embedded ARM computer. So everything's all in one: the computer and the radio, the entire system is all in one chassis. The USRPs have daughter boards for the RF front end, and that applies to the N series and the X series only. The B series and the E series don't use these daughter boards. And for these N and X series radios, the band that you want to use will dictate what daughter board you select. There are a bunch of daughter boards that are available. The main ones are the WBX, the SBX, the CBX, and the UBX with the frequency ranges you see there. The 40 and 120 capture bandwidths we can discuss later in the series. I won't get into that now. Most of the daughter boards have 1 transmit chain and 1 receive chain. The exception is this Twin RX daughter board, which is a dual receive only daughter board. There's 2 RX chains and 0 transmit chains on that daughter board. This is the basic architecture. It's probably hard to see. I can try zooming into the middle of it. Maybe that's a little bit better. I don't like this diagram too much because it shows the CPU and the FPGA as if they're on the same board or the same system, but they're not. This here is the host connection. So on one side you've got the CPU, the host computer, and then you have this interface that's either Ethernet, USB, or PCI Express. Actually, the X series supports PCI Express. And on this side, really the division should be here. You have the radio, so you've got the FPGA or an interface chip like a Cypress FX3 chip for USB, and then you have all the radio and daughter board circuitry over here. This square here is meant to denote the daughter board for those USRPs that use daughter boards, but basically all the A to Ds and all the tuners are on this side here. There's another diagram that shows it a little bit differently, and this is the general architecture of the USRPs. You have 2 antenna ports that you can use. One is for transmit or receive. The other is just for receive. And you have an LNA on the front end, and you have the up converters and down converters. You have the FPGA. You have the A to Ds and D to As, and so on throughout the whole chain. On the other side is the Ethernet or the USB interface. This is on the FPGA here, what's in the dotted lines. And this is on the motherboard, on the rest of the, on the RF front end and the motherboard of the USRP. We'll go into each of these stages in more detail throughout the series. For now, for the purposes of just ramping up and getting familiar with GNU Radio and getting something working, we won't go into this too much. This here is an overview of all of the USRPs, a different way of showing you how they compare to each other. That's probably not visible. And basically, it comes down to the interface and the sampling rates and the bandwidths and the frequencies of operation. So this bus series, this is shown with an enclosure, but it's basically this green board here, the B200 or the B210. They're similar. They're both the newest iterations of those boards are both green. This is the embedded device. This is kind of what it looks like. I don't have a better picture of it. I don't have one here with me. And this is the N series, and then this is the X series. These frequencies are daughter board dependent, but they're capable of, these 2 columns don't use, the E series and the B series don't use daughter boards, but the N series and X series, those frequency ranges are dependent on what daughter board you use. And they can capture up to 40 or 160 megahertz of bandwidth, and so on and so forth. You can read the rest. Again, the other big differentiator is the interface to the host computer, whether it's Ethernet 1 gigabit or 10 gigabit Ethernet or USB. And then there's LabVIEW support and MATLAB support and so on. They're all supported by GNU Radio. The MATLAB and LabVIEW support changes model to model. And then I have some pictures of the devices. This is a B200 Mini. It's the smallest one. I have one of those here. And I'll pass these around and someone can use that with their laptop if they want to. The N series and the X series, the inside and outside of the X series. I can actually get some of these, once we get going, if you want, I'll run over and grab some of these. You can look at them more closely if you're interested. And then these are the daughter boards. This is the UBX on the right, and then this is an SBX on the left. So that's the hardware, and then there's the driver for the hardware. And that's what we call UHD, the USRP hardware driver. And UHD is a single interface to all USRP devices, so you don't have to worry, other than within the limits of the hardware, you don't have to worry about what you're programming or what you're using. There's one common interface to it. The driver runs in user space, and it runs on the host. It runs on your CPU. It's open source. It's hosted on to modify it or change it for your application. It's cross-platform. It runs on Windows, Mac, and Linux. And UHD really kind of has three components to it. There's the host-side software driver, there's the FPGA image, and then there's firmware. And the FPGA image has to match the host-side software. So if you're using a certain version of UHD, that version has to be consistent both between the FPGA image and the host-side software. And this is the repository. I think I forgot the /UHD here. But github.com at its research, and you'll see the repository there.
When you say firmware, what do you mean?
So the firmware I didn't talk much about, but basically some of the USRPs use firmware, like the B series has firmware that runs on the Cypress FX3 chip. So there's also a firmware component. You usually don't have to worry about it because it gets loaded automatically. Usually what will trip you up is you might change the host side software version, but you don't change the FPGA version, and then when you go to run, it'll complain. And so you have to remember to go back and change the FPGA image accordingly. This is a diagram just showing that relationship of the driver to the rest of the software stack. At the lowest level, you have the motherboard and the daughter board, the hardware, and then you have whatever operating system is running. The E310, the embedded system, uses embedded Linux. It runs Linux. Then you have the driver, and then you have whatever framework or interface to the driver that you're using. Under the hood, all of these use UHD, regardless of what you're using, like MATLAB or LabVIEW or GNU Radio or OpenBTS. They all use UHD. And then your application sits on top. Whatever MATLAB program or flow graph you're running runs on top. And then this kind of starts some of the hands-on stuff. And the point of the exercise, at least today, to get things going, is to try installing UHD and GNU Radio and just make a simple flow graph. And so when you install UHD, there are a bunch of dependencies that you need, and those are listed here. These are, I think, other than Git, these are the minimum set of dependencies that you'll need to install. This should work for Ubuntu 14.04, which is what I have running here. I already got these dependencies, but if you want to follow along, you can try typing this and seeing if that works for you.
And we should add that we're going to put all these on the website, so if people want to try it later, all this will be there for reference.
Yeah, that's right. You don't have to rush and take notes now. You can download the slides later and go walk through them, go through them later. Yeah.
Do you have a link to the manual of some presentation?
I don't have a link to the manual of the presentation. I should have added that, so we'll add that when we post these slides.
So what version do you think we use for this OS?
Which version of what?
With the Linux distribution version.
Oh, of the Linux distribution?
Yeah.
It's Ubuntu 14.04. Yeah. And it's updated, so it's whatever the latest is. 14.04.03 with latest kernel and so on. I think I updated the kernel on this to 3.16, but yeah, Ubuntu 14.04 or the newer ones like 15.04, 15.10 all should work. Yeah, as well as Fedora and Red Hat 7. Red Hat 6 is kind of a pain, but Red Hat 7 should also work. Red Hat 6 is old. If anybody wants to go through this now, I can hand out a USRP, and you can try this and go through these commands. Anyone want to try this live, or try it on your laptops now? Nobody?
We can watch you demo.
You can watch, yeah. So if you want to, come on up and take a USRP. Your Commodore? I don't know if it's compatible with Commodores. Yeah, I have a cable here. Would you want to that one? Okay. Take that, and I think this cable should work. Oh, great. Okay, so. Oh, you know what? I don't have.
Here you go.
Okay. Run back and get some. We can take a 3-minute break. I'll run back and get some more. I don't even have one for myself. So to build this, we've cloned the repository. So now we're in UHD, and you can see the top level folders for each of those UHD components. There's firmware, FPGA, and the host. And so we'll go into the host folder and make a build folder. We'll CD into the build folder. And then we'll run CMake. And this is where we are right now. And the build tool for both GNU Radio and UHD is CMake, and we'll invoke it like this. That means go up to the parent folder and get the CMake list file. And it'll run, and assuming that all your dependencies are met and there's no components missing, all of these checks will pass and there won't be any errors. And it's a long list of things that get checked. But the key thing that you're looking for is this message at the end. You want to make sure that the enabled components include really all of these. All of these components here should be enabled. And there are some disabled components. And this is okay. The only thing you probably may care about is if you use the embedded E-series radio, you have to enable that separately. It's not enabled automatically. And so if you're using the E-series, you just have to add a command line switch to CMake to enable that. In this case, we're not using it, so we don't care that it's disabled. And my screen doesn't update, so I'm not seeing the same thing you are. So it says build files have been written to that folder. So now all the make files have been created, and so we can simply type make, and I'll try to accelerate this a little bit by including the J4 option.
Just do -J.
Or that.
-J60.
My system's not that good. It should only take a few minutes.
So if you use pi bombs, that would be effectively a way of checking out what you just did here?
Yeah, I haven't used pi bombs too much, but that is another way of building UHD. In fact, I think the next couple of slides will talk about that. Yeah, okay, so this is building from source, and there's a couple of good reasons to build from source. One is that you can change versions more easily than you can if you build with than if you install from a binary package. I'll talk about the binary package in a minute, but the good thing about that is with source you can easily change versions and rebuild. You can also easily build multiple versions side by side and run them. And also you can apply patches. So if there's a bug that you come across and we issue you a patch in the process of debugging the problem that you're seeing, you can apply the patch and build. You can't do that if you installed from a binary package.
I thought pi bombs were the claims to fame as well, and you run things side by side.
Yeah, pi bombs will let you do that too, because under the hood it's building from source. But I'm saying installing from a binary package, you won't be able to do that. So I think a couple of slides away somewhere, I thought I had some discussion about that.
I'm just trying to understand the trade-offs.
Yeah, right. I can't find it now, but I'm sure we'll come across it. But starting in UHD 392, we've added a Launchpad PPA, and so now you can build, install from a binary package. Before, what would happen typically, oh, thanks, Derek. Typically what happened in the past is, depending on what version of Ubuntu or Fedora or whatever you're using, when you would type yum install or apt-get install, it would install an old, usually ancient version of UHD, and that was a big problem because then people would install it, and it would install just fine, but then they'd go and try to run a radio and it wouldn't work. And we didn't have any better binary packaging system for a while. I think we do have RPMs, but we don't have Debian packages. But we do now. This works for Ubuntu. And so starting with 392, there's a binary package that's updated and built automatically for all recent Ubuntu releases for all architectures, 32-bit and 64-bit. So these are the commands you would use to install from binary package. Yeah.
Who maintains the PPA? Because I've requested. ARM 32-bit.
Well, I mean, we provide the PPA what to build. I mean, we maintain it in that sense. But I mean, Launchpad and I'm not sure who the individual is, but Launchpad handles that. Sorry.
We build the packages.
I thought they build it. We supply the source. Yeah, and they build it. So I mean, in that sense, they maintain it. But I mean, if you wanted to ask about something, Martin would be the best person to talk to, the person who spoke at the beginning. Yeah. So this thing is almost done. Okay, so that finished. And so the next step is you could do a make test. I'm going to skip that, and I'm just going to do the install. Oh, somehow.
Is a specific release to do, or I can build from?
Oh, you can. I would. Generally, we recommend that you use a tag release. So yeah, stick with like 391 or 392. But yeah, you can certainly build from master. Okay, so it installed, and then I'll do an ld config. Too many O's. Okay, config, and now it should be ready, and so I can try using some utilities and see if they work. And so I've got this B200 plugged in, and power light is on. And so it should work. Now, one thing with the B series, I didn't put this in the slide, but I'll just mention it. I can go back and add it. I probably should. Is sometimes when you have trouble with the USB radios, it can be a result of your USB controller. And so it's always good to know, to be able to find out what your USB controller is. If you type LSPCI, it'll usually report to you, and you'll be able to figure out which one is your USB controller. And in this case, I have an Intel 8 series. And most of the Intel USB controllers work pretty well, like the 6 series, 7 series, 8 series, 9 series. I think there's one called a Wildfire. What was the name of it? Wildcat. I think that worked pretty well. So that's how you can check your USB controller. And then I'll give this a try and see if it works. And so when you run any UHD utility, it'll report to you the version number up at the top. So I know I'm running 392, so that's good. That's what I just built. And it found my device. It's a B200. You can name devices. You can put a name to it. I think from the factory now they just call it my whatever. I think this is a relatively new thing, but you'll see this come up probably if you have a recent device, new device, you'll see this. And then the serial and the product number. The type is like a family, so for the B series you'll always see B200, but the actual product is the actual device in that family. So if I had a B210, it would say B210 for the product, but the type would actually be B200 still. So don't be confused by that. There's difference in meaning there. All of these settings, by the way, these parameters are stored on an EEPROM on the motherboard, and you can query them separately. And if they ever get corrupted, it can cause you a problem. There's another command called UHD USRP probe, and that will tell you a little bit more about. There's a lag between what I type, what appears there, and what appears here, and so it's really hard to use this.
You're off by what?
Yeah, and the character still hasn't appeared yet, so I don't know. Okay, there it is. There's literally like a 2 or 3 second lag.
Do you think
This
it's X11?
Yeah,
I mean,
it has to
VNC.
be. I'm just gonna. It's responsive there for the most part, but here it's like,
Just turn your whole desk.
yeah, it's like I'm typing to halfway around the world and it's coming back. It's like I'm SSH'd into a server on the other side of the planet. Okay, so I run the probe, and I'm reassured I'm still running 392, and it detects my device, but now there's a problem. It says FPGA compatibility number 13, blah, 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 blah. So what does all this mean? So it kind of tells you what to do to fix this. It says, please run this, but what is that? So what's happening here is, apparently the FPGA is using an image that was with an older version of UHD versus what I've just installed, which is the latest version, 3.9.2. And so there's some incompatibility there. So it's telling me to download the images, the latest set of images, for this version of UHD that I'm running, and install those locally on the system. And this program will do that. You usually have to run this as root, so you should put sudo in front of this. And I'll go ahead and run this like it suggests. And it'll run and download from this site here, this URL here, the latest set of images for UHD 3.9.2. And it'll unzip them and expand that archive, and then it tells you where it puts it. By default, it puts it here. This is why I had to run it as root. And now I'll power cycle the device. I'll just unplug it. There's actually a reset button on the device as well, but I'll just unplug it, and I'll plug it back in to clear the FPGA, the image. And now if I run probe again, it'll load the firmware, and now it'll try loading the image, the appropriate image for the version of UHD that I have. Okay, done. Yeah.
Just make it narrow.
Yeah. Okay, and now it gave me back what I was interested in, all this output here. And it'll tell you everything about your device, whatever device it is. It'll tell you what features are installed, like a GPSDO, what interface it's talking over, what kind of clock rates are available, what kind of clock rates are set, what kind of daughter board is in there, what the serial number is, what revision of the board you have. In this case, I have a B200 revision 5. Interesting to note that some of the B200s you might have seen are white and some are green. The white boards are the older revision 4 boards. The newer ones are revision 5. The B200 also has a revision 6, which has a, I think this was mentioned in the beginning by, I think by Tripp when he gave his presentation, has a different analog devices part on it. Same functionality, but a different model of it. And this will tell you all the frequency ranges that are supported and so on. It tells you everything about the USRP and its capabilities. And the fact that that works means, the fact that this command works means that I'm able to talk to the device, and I'm fairly certain that things are working properly. It doesn't mean the whole device is completely, all the hardware is completely working correctly, but at least the host can communicate with it and interrogate it. And so it's a good sign, and it means that so far so good, the device is working. And that's what I've captured here in the screenshots. You have UHD-defined devices with some example output here. In this case, I'm using an N-series device. There's no name pre-programmed and a different serial number. And then here's the probe across 2 pages here, 2 screenshots. And there's the images downloader that we saw running and downloading the images. And there are some other utilities. As the series goes on, this tutorial series goes on, we'll go further into this stuff. This is kind of esoteric. We don't need to worry about it now, but I'll mention that if you look in the examples in the utilities folder in the UHD source code distribution, you'll see a whole bunch of programs. There's a couple that are good to know that are there. For the X series, there's a utility that'll burn the FPGA, that'll flash the FPGA. And then there are two utilities for reading and writing the EEPROM on the motherboard and the daughter board. And that can be critical sometimes, so that can be really important to know. So those utilities are in that folder here. By default, they're in this folder. I should also say that if you want to install UHD or GNU Radio in a different folder, you can certainly do that. There's a command line option for that, and maybe we'll talk about that in the next part in the series, the next session. UHD ships with a bunch of example programs, and these are C++ programs that use the UHD API directly. You can use these as a model or a template for your program that you might write, or you might just use these utilities straight from the command line to do something. At this point, we haven't installed GNU Radio, so we don't have that yet. So we only have UHD, but even with UHD, there are some utilities we can use to verify that the radio works or make it do something. And you see those listed here. I won't go over these in detail just because time's it's getting late and we want to try to get to GNU Radio and maybe run a flow graph. So I'll spend more time on this in the next session, but you can read this slide and see there's a couple of utilities that are useful, and example command lines here are given. And this is how you specify the frequency and the sample rate, the gain, and so on. And you can transmit or record from the radio to a file and look at that output. Or one of these utilities is interesting. This ASCII art DFT utility. It basically is an ncurses based, a console based real-time FFT. It's obviously not as pretty as all the other utilities that are out there like GQRX or Baudline or Phosphor, but it's a great way to just quickly get a sanity check when you don't have those tools installed yet to see whether the radio is working. And so you can inject a tone, run this, and if you see your tone, you know that the receive chain is probably working. It's also useful when you're SSH'd into a computer remotely. Sometimes you use these things in labs and the device might be down the hall or something like that. You don't want to walk down the hall, or you just want to see if a signal is still there because it's configured in some test configuration or something like that. And so you can quickly, if you don't want to, VNC into the machine or something, this is a quick and dirty way just to see if a signal is present or not. And then these are screenshots of those other utilities running, and I'll skip those for now, but you can look at the screenshots and see what they look like. This is recording samples to a file on disk, and it just runs for however long you tell it to and writes files. You can look at the others separately. And then this I'll also skip over. This is how you use the API directly, and you can see all of this code. It's all in the examples folder, but we'll go through an analysis of this at a later time in a future session. There's also the Wireshark tool, Packet Sniffer. I'll talk more about this in another session when we maybe use an Ethernet-based radio. The radio I have here is USB, so this wouldn't be quite as relevant. I mean, we can sniff USB as well, but there's a couple of things I'll point out with this, but it's more specific to Ethernet interfaces, so I'll skip it for now. And then GNU Radio. So let's dive into that. What is GNU Radio for those of you who maybe aren't clear or don't know? So it's an open source framework for SDR and for signal processing. It was founded by Eric Blossom actually quite a while ago. Sometimes people don't realize how old it is, how long it's been around. The current project leader for GNU Radio is Tom Rondeau, and it's basically a block-based data flow architecture. Each block in what's called a flow graph or in a flow graph runs in its own separate thread. It's kind of like Simulink. GNU Radio is free and open source. It's hosted on GitHub, and there's the web page. Before I get into building it, I'll just say one other thing. Actually, let me hold that. Let's go ahead and try building it. And again, there's a whole bunch of prerequisites, a little bit longer than for UHD. Some of these are graphical in nature because GNU Radio has GUI widget components to it, and so you'll see a lot of Qt and WX dependencies here. All of these should already be installed on my system. I I don't know if you want to race and try typing all of this. I doubt it. So, maybe what I'll do next time, I think this time we posted maybe a little bit late the idea that you could bring your own computer and USRP and kind of follow along. Next time we'll plan that better, more ahead of time so people can be prepared. And I'll hand out some text files or some scripts that will have all this. You don't have to sit there and type it all, because that's a lot to type on the spot. And that'll make it easier to follow along. But I'll go ahead and build GNU Radio quickly, and it's the same idea. I'm going to start in a new folder. And I'll just do a git clone. Now this time I need this -- recursive option. You don't want to use that when you're building GNU Radio, UHD, but you do want to use it when you're building GNU Radio. And the reason is there's a component called Volk, V-O-L-K. We'll talk more about it as the series progresses, but basically Volk is an optimized, assembly level optimized library for signal processing functions. And it is broken out into what's called a submodule. And so if you don't say recursive, it won't know to get that submodule. But that submodule is required. So that's why you need the recursive there. Oh, wrong window, sorry. And so I'll do the clone for Git. Sorry, the clone for GNU Radio.
If you have an easy way to send me those slides right now,
Yeah.
I can post them.
How could I do that? I don't have email up at the moment. I can SCP them to a folder or something. Or you can SCP them out. Yeah, okay, we'll just do that later. I'll do that right after the talk ends. Man, this display is horrific.
We'll work that out.
Okay, so the clone completed, and the rest of the process is pretty similar as for UHD. So at this point, now I've got a folder called GNU Radio. Wow, this is slow. It literally is a 3, 4, 5 second delay from whatever I type. So these are all the folders that come in the repository. As we did with UHD, I'll make a build folder and I'll CD into it. And I'll run CMake as we did before.
Forgot to select those.
Yeah, that's true. I didn't do that, and so right now I'm working off of master, and probably to be safe, I should choose a specific release. Let's go ahead and do that, and I'm just going to brute force this and blow away my build folder. I'm going to remove recursively the entire folder, and I'll just do a git checkout of 3.7.9. And then I'll repeat those steps and make my build folder, and then just go back and do another CMake now with 3.7.9. And just like here, I just ran this command and repeated this step here. Okay, and the configure completed. All these components are built, which is good. Most of them you either want or will need, or there's no reason they shouldn't build. This one you don't need, and you probably almost will never need it, and so that, given that it's disabled, that's fine. And then we'll do a make, and now build GNU Radio. This will take a little bit longer than UHD. Let's see how long it takes. While that's running, I'll keep going forward in the presentation. The last step is the same LD config, and then GNU Radio should be installed. There are other ways to build GNU Radio. You can use PyBombs, as Martin talked about at the beginning of the evening. New version 2 is just out. I haven't used PyBombs myself, but yeah, it's the bomb. I know a lot of people, praise it, and I think a lot of the changes that Martin mentioned in version 2, I think make PyBombs a really powerful tool. As he said, it's basically like a RPM or a PIP for Python, like a GNU Radio package management system. So it makes out-of-tree module is a lot easier to build and install and maintain.
We should cover that in the future.
Yeah, that should actually be like a whole topic in the series. So we'll talk about that. Yes, go ahead.
So he talked about the plugins out of the tree.
Yes.
The pipelines. So if I build the generator like we're doing now, I am still possible to get the plugins installed.
When you say plugins, you mean the out-of-tree modules?
Yeah.
Yeah, if you don't have to use PyBombs to get those. That's right. Yeah, PyBombs is completely optional. Yeah, if you want to install out-of-tree modules, you can just do it from the command line using the same tools like Git and CMake and that kind of thing. I have a slide about that actually coming up. Yeah, you don't have to use PyBombs.
But you can use PyBombs if you want to install out-of-tree modules if you have manually installed GNU Radio already. You just have to tell it that you've already installed GNU Radio. Because it tries to satisfy all the dependencies. If you tell it when you configure it that that's already installed and satisfied, then it won't do that and it'll just use what it wants.
Another way to build GNU Radio is with this build GNU Radio script. And this is something that Marcus Leach created.
Who presented for us last time.
Who presented for us last time, you might remember. Radio astronomy presentation that was really, really cool. He runs or ran, I think it's not in operation anymore, but the Shirley's Bay Radio Astronomy Consortium, SBRAC, up in the Ottawa area. So thanks to Marcus Leach for creating this script and maintaining it. His script will build UHD and GNU Radio from source. I don't think it handles out-of-tree modules, but just for getting up and running with GNU Radio and UHD on almost any Linux platform, Red Hat or Fedora or Ubuntu, the build GNU Radio script will work, and you can invoke it with this command line here. The whole command line is in the slide, but you can run it from this command line, this one line, and it'll kick off. The only thing though is there are a lot of options, and so you should do a -- help and look at the options for this, because build GNU Radio lets you specify a specific tag, a specific release for UHD that you want to build, or a specific release of GNU Radio, and a whole host of other options. And so it's worth looking at that. You probably don't want to invoke build GNU Radio without any options, but it's a really powerful, really useful script. What it basically does, though, is what we're doing here, building from source. And then finally, there's PPAs. The problem with the PPAs is that a lot of them are old and out of date. And so for, say, Ubuntu 14.04, which a lot of people use, and it's an LTS release, it's a pretty old version, 3.7.2. That's the default. With newer versions of Ubuntu, like 15.10 is the most recent, you get a fairly recent GNU Radio, but usually people might be on an older version like 14.04, which is an LTS release, and then you're kind of stuck, or at least by default you're stuck. You have to change where you get it from. And it's not something that people maybe normally know how to do or do automatically. And so more likely than not, if you just go and type apt-get install, you're going to get an old version of GNU Radio. And so it's probably better to build it from source, or to use the build GNU Radio script, or use PyBombs. But these are all the options. These are the 4 options for building GNU Radio. Once it's built, you can use GNU Radio to verify the operation of your USRP. We saw how to do that in sort of a basic way back here using UHD, meaning using only the driver directly. Not using any GNU Radio stuff. And there's a couple of utilities that I mentioned that you can use to do that. But once you have GNU Radio installed, there's a lot more you can do, or at least a lot more you can do easily. And there's 2 utilities that come out of the box with GNU Radio that are graphical in nature, and you can run right from the command line. There's UHDFFT, which is a spectrum analysis tool, and this is a screenshot of it. So this is obviously better than the RX GUI with the ncurses display, the console display. So this will show you clearly whether your USRP is operating correctly. If you see a tone, for example, in the right place, you inject a tone using a signal generator, and then chances are that your receive chain is working. And then you can do the opposite and generate a signal. There's a command line version of this tool, UHD SIGGEN. You can specify a waveform and a frequency and so on to transmit, to generate. And there's a GUI version as well that you can use. And when you're doing these things, whether transmitting or receiving, be mindful of the things that can trip you up and make you miss the signal. Things like where you're tuning to, your sample rate, which antenna you're using. On this B210, there's two sets of antennas. So sometimes you may not be aware of which one you're connected to and which one you selected in the GUI. So be careful of that. And then also the gain setting. I think in a lot of cases the gain is by default 0 dB, and depending on the signal that you're injecting or the signal you're transmitting, it might be very low. So be mindful of those things. Yeah, GQRX uses GNU Radio under the hood, but it's not built automatically. You have to build it. It's a yeah. So GQRX under the hood uses Osmo. What is it called? Osmo. What is it?
Osmo SDR.
Yeah, Osmo SDR. Osmo SDR. So you have to install that first, and then you can install GQRX. I have a slide about that. We'll talk about it in a future session.
But the driver is also UHD. Everything goes through UHD. It's just to have GQRX, it needs GNU Radio, and then you need UHD, and then there's a separate out-of-tree module called Osmo SDR that wraps up, USRP, RTL, everything else under the sun.
Okay, this is GNU Radio Companion. Once we run these utilities, the next step is to actually bring up GNU Radio Companion and make a flow graph. GNU Radio is still building on my system. It's 2/3 done, but I can show you some slides quick about what that looks like. So GNU Radio Companion is a tool that lets you graphically place blocks on a canvas, kind of like Simulink, and wire them together. And the blocks, wish I had, look like this. Every block corresponds to a construct or an item in Python. Underneath the hood, what this tool does is generate what's called a flow graph, and that's basically a Python program. And each one of these blocks is a Python element, whether it's a variable or even this options block, or there are other blocks you can specify. They correspond to items in Python. And you create these and use the blocks from a library of blocks that appears over on the right, and you drag and drop these in and you connect them. And when you connect them, the connectors, the ports, will be colored. The colors indicate a data type. And you can see the data types by clicking on types and then getting a color mapping. And that'll show you the legend, the mapping of color to data type. And for some blocks, you'll see a different color on the input than the output. Other blocks, it'll be the same, but you have to make sure that everything matches. If something doesn't match or something's miswired, it'll appear in red, and you'll get an error. And once you have your flow graph constructed here, you click this button here to compile the flow graph, generate the Python code, really is what it's doing, and then run it. And that same Python code can be invoked from the command line under the hood. We'll show you examples of that. And the blocks all have properties. If you double click on the block, the properties come up. The properties for the USRP source block are shown here. USRP source would be a block that's giving you samples. The USRP is a source of samples, so you're receiving something. And the properties for that block are shown here with tabs, and we'll go through this. Before we go on, I'll ask you guys about time. It's already 9:45. Should we stop here and continue in the next meetup? From this point, or do you guys want to keep going a little bit longer, or what should we do? Maybe go till 10. Just call it at 10 o'clock.
Is the next meetup going to be in SF?
Yeah, we do still alternate. Yeah. I mean, I don't know that the next one of these sessions would be in SF. It would be next month. Maybe it'll skip a month, but I don't to be determined there. But Why don't we just go till 10? It's getting late. I'm sure some people have to leave, or people are getting tired. So why don't we go another 10, 12 minutes till 10 o'clock, and we'll stop. Yeah, it's almost done. Hopefully it's almost done. 81%. Yours is what, 66 you said?
56.
Okay.
But what's to my brother will die before.
Oh, okay. Well, that's not going to help. What's that? Do next time? Okay. You know what? This probably actually is a good stopping point, because even when this build's finished, it's going to take at least 10 minutes to get into everything and show something and build a flow graph. So maybe this is a good spot to break. So why don't we stop here, and I'll just give you a quick preview of what we'll do next time. We'll build a couple of flow graphs. You saw from some of these slides. We'll go through.
Someone said on IRC, go till sunrise.
Go till sunrise. Oh, I don't know if I have enough material, enough slides created for that.
Yeah, exactly. What time zone is he in?
Yeah.
Ah.
We'll be there quite soon, actually.
Well, if it's Europe, it's already just about sunrise. But so we'll next session of this ongoing series, we'll look at these blocks and explore the properties for all the common blocks, such as these ones here, signal sources. There's not a USRP signal source. This is just a signal source, a stream of samples. We'll talk about these throttle blocks and why they're necessary, and we'll look at the various GUI widgets for time domain plotting and frequency domain plotting using the Qt library. This is a screenshot of that. We'll look at another flow graph, a little bit more complicated, showing some other features and capabilities of GNU Radio, showing some of the other blocks in use, like noise sources. And then we'll use a block with the USRP. So now this block is a USRP sync, so it takes in samples, meaning it transmits. And so we'll show a transmission, and I'll show you some of the underlying code and how that works. That's a screenshot of a text editor showing the underlying Python code for this flow graph. And then we'll look at some FM examples of doing FM transmit and receive. And then we can have some fun kind of playing transmit and receiver. And we'll look at the waterfall to see who in a group. Hopefully, maybe more of you can bring your laptops and USRPs with you. We'll bring a few as well, a few extra devices. And then each of you can transmit on a different frequency. And then on the screen up at the front of the room, we can see who's transmitting and see which FM channels are active, and kind of go back and forth and flip it around where you become the receiver and I become the transmitter. So we'll do some of those exercises with FM using GRC, and that'll probably take up most of the next session. And I think Martin mentioned this, but that's CGRAN, and then GQRX, and as well as RDS. So we'll see how far we get next session, but that's the plan for next time. So tune in then, pun intended. Sorry we got bogged down and we didn't quite get to the hands-on, even though it's advertised as hands-on, but I think we started late and then ran out of time. But next time, tune in.
We're going to finish just as the build finishes.
I know.
Well, that's a good place, because next time then we can...
Everything will be ready.
Everyone's got a working build.
And we'll put the slides up. I'll put these slides up so you can kind of catch up to where we are. Okay, questions? Yeah, Derek, sorry, you had your hand up.
So if somebody was installing this and they got stuck somewhere, is there a handy mailing list that they can go and ask questions on?
Yes, so if you have any questions about things that relate to USRPs in particular, there's on the web?
Yeah.
Okay. So John Pendlum. Yeah, John Pendlum has a landline and a mobile number. I'm going to give you both. And sorry, John, what was your satellite phone number? So we can reach you when you're on vacation.
So Neil is 6.
I don't know why it's giving me the security and stuff. So there's 2 mailing lists, and the mailing lists are usually pretty responsive and a great place to get help, and a lot of people in the community are pretty active on it, so you'll get all kinds of feedback. The first, yeah, I will. Yeah, right. The first mailing list is USRP users. If you just Google that word, you'll find it. But we'll put something on the website to point you to it. You can subscribe to it. All these are completely free. Everyone at Edis and for the GNU Radio one, the GNU Radio community, all monitor this. And you can post on this and ask for whatever help or question you have. And the archives are pretty good. There's a whole long listing of all the past discussion going back actually years. If you look at this, going back to 2010. So you can. The search is not that great. If you try to Google stuff, it's really a pain. It's something we know about, and hopefully we'll.
There are archives at marc.info, marc.info.
Oh, okay. That.
Much nicer search. MARC.
Okay, got it, Mark. Okay, I'll take a look at that.
Just search for USRP on that page and you'll find me.
Oh, yeah, I saw your post about that. Yeah, I forgot. Yeah, thank you. Thanks. Yes.
Hey, finished building!
Just in time. So that's the USRP Users Archive, and you see all the traffic there. And then there's a corresponding one for GNU Radio. Yeah, well, he's active on both. Marcus Mueller, Marcus Leach, they're active on both. Same thing, you have the archives here. You can sign up for free. There's a fair amount of traffic. It's pretty active, and same thing. You can search these archives or use marc.info, I would imagine. So those would be the two places I'd go for help initially. Discuss GNU Radio and USRP users. There's also an IRC channel, #GNU Radio. I'm not sure how useful it might be for help, but certainly a lot of people are hanging out there if you have a quick question or need a quick answer, that kind of thing. There is a #USRP channel, but it's pretty low traffic. I think anything relating directly to USRPs or UHD or the hardware, you should put on USRP users. Anything relating to GNU Radio or installation problems with GNU Radio or flow graph questions or signal processing questions probably belong on Discuss GNU Radio. Any other questions? Okay, well, I hope you enjoyed this.
If you built it, just install it and run.
Okay, sure.
Open GRC.
Yeah, sure.
Give us that satisfaction.
So I'll do the install.
The thing that takes the longest is the. Oh no.
No, the install's pretty quick.
do config info.
Yeah, right. Okay, so there's a good, useful utility here called GNU Radio-config-info. It'll tell you all kinds of information about your installation. I mean, simple one is just the version, and so on. I mean, you can see the output here. So this is useful if you need to get any configuration information. And then here's GRC.
Yay!
There it is. And so you can take blocks. You can hit Control F here. We can get signal source. Bring it over. You can move all these things any way you want. You can double click on the thing. Every block has properties. Most of them have multiple tabs. There's different properties and documentation. And the documentation. So there's for UHD. If you go to uhd.edis.com, you'll get to the UHD and USRP. I don't know why that's happening. We try to slip a Trojan. I don't know. So this is the USRP and UHD manual, and then on the GNU Radio page as well, they have some similar documentation. So you can go there, and then.
It's that you don't have a wildcard cert installed, so
Is that Google telling you that the website is not HTTP?
No, it's Firefox. So this is Firefox 44, I think. I don't know why. I noticed with 43 just a few days ago it wasn't doing that, and then today it's doing that. I haven't had time to think about it, but anyway. So these are different blocks you can pull in, and you can connect them. Doesn't really make sense to connect two sources, but
Get an ad.
yeah.
Somebody upgraded your website's certificate and didn't put the wildcard in.
Okay, thanks.
Probably don't tell what data it is.
Yep.
So you just click on each port, and then you click on the other corresponding port you want to connect to. In this case, they're both the same data type, so there's no conflict. Nothing's highlighted in red. But I could go here and change the type, and now it's expecting a different. That color is hard to see, but it is a different color. Now that type is different from this type, and so these two arrows appear in red. And that's GRC, and you know, that's the 5-second introduction to GRC in a nutshell. Okay. Oh.
QT.
Oh, okay. Yeah. Sorry. Let's do that. I'll do. Where is it? Where's my QT?
Frequencies.
It's okay. I'll just use this then. So I'll connect these, and I'll set a cosine at 1,000 with a sample rate of 32K. Most of these should be all fine. FFT size at 1024, and
Your top block is in QT.
oh yeah, set that to W. I'll explain this next time.
WX, yes.
And then, yeah, I'll call this test
Long
one.
live WX.
So this is generating for Python.
Oh, yeah.
Just run it. What happened?
I need a throttle block.
There you go.
I don't really need one, but well.
Next time we'll cover throttling. We don't need it. There we go.
So there's my FFT of my perfectly constructed signal source
At 1 kilohertz.
at 1 kilohertz.
Increase the dB per division. I want to see what your floating point noise for is.
No, you can't.
It's not possible.
Right.
Yeah.
Next time.
Next time. Okay. That is all for today.
Oh, Patch Bond Bronze said, don't forget the throttle block, Neil. Okay, put the throttle block in there.
So quick question.
Thanks, Marcus.
Is there anything you could do in a Python script you can't do in the GUI or vice versa?
No, I mean everything, whatever you construct in the flow graph gets generated in Python. So no, I mean you can do everything. I mean everything is running in Python. So.
But the other half of the question was, is there anything can you do in Python that you can't do in GRC?
Oh, yes. So that's another whole part of what we'll talk about over time. I mean, in Python you have the whole Python environment. I mean, say you wanted to configure. Yeah, exactly. Say you wanted an XML file to define your transmit frequency, or you had to, you had a server, you want to connect a socket to it to get some information about something. I mean, all of that you would do in Python. You wouldn't try to do that in the flow graph.
Can you do it in a hybrid mode where you can do as much as possible in GRC and then integrate your own Python?
Yeah, no, absolutely. It's not really a hybrid mode. It's more you do as much as you can in the flow graph, or maybe for debugging purposes for the core algorithm, it's useful to do it in GRC. Once you know that's working, then you can add all the other control logic or file parsing.
From the flow graph to your,
well, so every time you regenerate the flow graph and you run it, it'll overwrite the Python file.
But you can import that.
But you can.
Call Python from the flow graph.
Yeah.
Way beyond the scope.
no, I understand. A lot of graphical interfaces end up being an either or. It's sort of like it generates the code.
You can generate a Python module with this, and then you can have a higher level application that can import this as a module and make it do stuff. That's one way to do it. The other way to do it is that you can inject code into this. So you can have like your own little blocks defined in Python, and then you can inject it into the flow graph, and then they'll work side by side.
Cool.
So lots of options.
Oh,
Yeah.
You can write custom blocks too.
Yeah, they're not mutually exclusive. You can use both. Yeah.
But it does
Yeah.
require. Yeah, custom blocks is an apt.
Okay. There we go.
Hey, 170, negative 170 dB.
Or is it single precision?
Yeah.
All right. So
Okay. Yeah, it's 10 o'clock. We can we'll end here, and we'll see you at the next one.
thank you, Neil.
Thank you, guys.